I have a privilege of introducing Dr. Nagesh Kumar. He was formerly director of in NPC Chennai, director of energy efficiency. He spent almost 30 years in NPC before he left and formed his own company. And we have done a lot of studies together, lot of energy audit together all over the country. So he has already presented case studies in earlier webinar, which was appreciated very much and overran time. Now we are again introducing him to present case studies in pumping system. And pumps are more than just pump energy savings, more than just application of variable speed drive or trimming the impeller, as you will conclude after listening to the Dr. Nagesh Kumar. Welcome, Dr. Nagesh Kumar.
Thank you very much.
And you can talk and start the proceedings. Also welcome our Director General, Mr. Arun Kumar Jha, who is also with us to listen to the webinar and give his feedback and appreciation at the end of the webinar. Thank you, sir, for making your presence.
Okay, thank you, Suryanarayanan, and very good afternoon to everybody. Good afternoon to our Director General of NPC, Mr. Jha, and other participants who are viewing this presentation over the internet. So today we're going to talk about how we can save energy in the pumping system. In the previous session, we had talked in general about how energy efficiency is actually achieved in the end use. And today we are talking with specific reference to one particular equipment and system, that is the pumping system, the pumps and the pumping system. So the pumps, as we all know, is another ubiquitous equipment you'll find in almost all sorts of industries, right from a simple pumping water to the overhead tank, to megawatt range pumps which are used for the process purposes. So in power plants, if you see the several megawatts of power pumps which are used for the cooling water circuits, the boiler feed water pump. So the range of pumps that we encounter in the industry is pretty wide. But nevertheless, the concept, the approach to energy savings remains the same irrespective of the size of the pump, the type of the industry where it is applied. So as we discussed in the previous sessions here, the pumps are important, no doubt, but what we are going to focus is on the system. So how the pump interacts with the system. The system is everything other than the pump, the piping, the footwall, starting from the footwall, the suction pipe, the discharge pipe, then the water that is going into a process to the heat exchangers, the pressure drop across the heat exchangers. So everything other than the pump is a system. And the pump is the equipment we're going to talk about in addition to the system. So as we know, here is an electric motor which is driving a pump, and the pump is discharging some water at a particular pressure which is required for some process purpose. Now, what determines the power drawn by the motor? So as we have seen earlier, it is not the motor which determines the power. It is basically the amount of water that is required to be used and the pressure at which it is to be used. That determines the power of the pump. This is the output power of the pump. This is the power to be delivered by the pump. And the input power to the pump depends again on the efficiency of the pump. So there are some losses in the pump for which the input power needs to compensate. So the input power consists of some losses in the pump and actual power, that is the hydraulic power that is delivered to the process. The losses in the pump may range from anywhere between say 25% to 50%, which means the efficiency of the pump itself is rather low compared to the efficiency of the motor. The efficiency of the pump, as you see in normal practice, on the average, it could be around 65%. So about 35% of the power is lost in the pump itself, which is, of course, going off as heat. The amount of water that is going into the pump takes off this power as heat, and then it goes out along with the water. So when we talk about the efficiency, this is the pump efficiency. 65% is coming out as a percentage of input power. And then what happens here? Where the water is used, how much water should be used, at what pressure it needs to be used. So all this will determine the overall efficiency of the system. Okay, so now we'll start with discussing the pump itself. As we said, the most important thing is the selection of the pump. If the pump is rightly selected, then throughout its life cycle, we have very little loss due to energy. But if there is a bad design, that means a mismatch between the pump and the system, then we are going to incur a huge amount of money for compensating the loss. So we'll go through the basics of the pump first. This is typically we are going to talk about the centrifugal pumps, which are quite common in the industry. Almost 95 to 98% of the pumps used in the industry are centrifugal types. So it's a very simple piece of equipment. There is a casing, outer casing here. Inside this, there is an impeller which is rotating. So driven by the motor, by the shaft. The impeller rotates, imparting velocity energy to the water. So the suction is from the center. So the water goes from the center here, and then the impeller rotates, giving the water a high velocity energy. So the water carrying high velocity energy, as it tries to leave the pump, we find that the area of the casing is increasing. This is called the volute section of the pump. So why the area should increase? The reason is that if the area increases, the velocity decreases, the velocity energy decreases. So the total energy here, what is coming in the form of velocity energy plus a little bit of pressure energy, because of reduction in velocity, the velocity energy reduces, and that velocity energy is converted to pressure energy as the water comes out through the discharge. So this is a simple operation of a centrifugal pump, where the velocity energy is converted to pressure energy in this section of the volume, that is the expanded area. Now, if you look at the characteristic curves, this is a very important as far as evaluation of pumps is concerned. So you will find that in many of the cases or in the industries that these pumps are originally supplied along with the pumps, but they go missing quite often. So you don't get to see these curves in the industry. When you go to the industry, the pump is there, but these pump characteristic curves are not there. So it's very important to keep a set of these pump curves as it is given by the manufacturer. The first thing is to demand these curves from the manufacturer when you buy a pump. The second thing is to store them safely so that it will be made useful for the later on analysis. If you look at the characteristic curve of the pump, this is the characteristic curve, the head versus flow. So this curve, the characteristic curve of the pump, and on the y-axis you have the term called head, and here on the x-axis you have the flow rate Q. So what this curve tells us, suppose you have a pumping system like this. You have a pump, and then you have a pipe, then a valve. So as you keep closing the valve, what happens to the pressure? So there's a pressure gauge here. So the pump is operating. So valve is fully open. When the valve is fully open, that means maximum flow is obtained. This is the operating point. As you keep closing the valve, we are actually offering a resistance to the flow. That means the pressure is going to increase. The head is going to increase. So the head keeps on increases. As we keep closing the valve, the head keeps on increasing. And now we come to this operating point. So this is the characteristic curve of the pump. The more the head, or the head here basically refers to the system resistance. So what is the system resistance? This pipe is going to a set of heat exchangers here. So maybe this is a system. So you have some heat exchangers and water is going to a cooling tower, maybe. So you have a cooling tower like this. And the cold water is coming back to the pump. So this is the system. What is the resistance offered by these pipes, the heat exchangers here, and the vertical lift that is going to take place in the cooling tower? All this determine the pressure against which, or the head against which the pump is going to work. So the higher the head, the higher the resistance, the lower will be the flow rate. So you can see here the head goes up and the flow rate comes down here. The next curve, what you see is the efficiency. For various flow rates, we have this efficiency. And the efficiency curve, you see, it's quite unique again. You will find that the maximum efficiency of the pump occurs at one particular point, that is at this flow rate. So at this flow rate, you will get the maximum efficiency of the pump and against this head. If you look at a motor, electric motor, the characteristic curve, efficiency versus load of the motor will be like this. So it'll keep on going up, and maybe after 50% load, so this is at 50%, 50 to 100%, the efficiency of the motor remains the same, doesn't change. So even if you oversee the motor, it is immaterial, it doesn't matter, it doesn't affect much. But in the case of the pump, if you select this particular operating point, this flow you're going to select, and at this point, the efficiency is maybe about 65%. And you want to now operate at a lower flow rate. What will you do? You will throttle this valve, increase the head, and lower the flow rate. Flow rate is now lowered. What happens to the efficiency? So here, if you see, the efficiency might have come down to even 40%, depending on the characteristic of the pump. So from 65% efficiency, the pump has come down to 40% efficiency, just because we have oversized the pump. The pump is rated for this flow. Now we want to operate at this flow. So there is a dramatic reduction in the efficiency where we are losing quite a considerable amount of power. The funny part about the pump is we don't know where we are losing the power. If you go to the industry, the process people say it is an efficient pump. What is an efficient pump? For them, as long as the pump delivers the required quantity of water at a particular head, it is an efficient pump. Nobody knows what is the efficiency of the pump, at what efficiency it is operating. Whether it is 65% or 40% or 30%, nobody knows. Because the pump is anyway meeting the requirements of the process. So nobody is concerned. So these are what are known as hidden losses. We don't know what is happening. The requirements are delivered by the pump, but at what efficiency, nobody knows. See, if it is a lighting, for example, some lamps are on and then nobody is there in the room, it's obvious. Visually, you can say that there is a loss. In this case, unless you measure various parameters and find out what is the operating efficiency of the pump, it will not be possible to determine how much energy we are losing by not operating at the best. This is called the best efficiency point, 65%. So when it comes to a pumping system, we need to bank on some measurements. We need to measure the power, we need to measure the flow rate, we need to measure the pressure, discharge pressure, suction pressure. So these are some of the basic ingredients that go into the audit of the pump systems. And the third curve, what you have here is the power curve. So the power, as you can see, it keeps on increasing. The more the flow, the more will be the power. So these are three most important curves that come along with the typical pump as it is sent by the manufacturer. Then there is another requirement from the operational point of view, which is NPSH. Will not go into in this session. So the hydraulic power, that is, if you have a motor, electric motor is there, then you have a pump, and pump is delivering some water here, output. So what is the power in the water? This is called the hydraulic power. So it is an mgh. Q is the total head, which is discharge head minus suction head into the density into the gravitational constant by 1000. This is a hydraulic power, this is power in the water. To deliver this much of hydraulic power, what should be the input power? That means the power at this point, input power to the pump. So this will be the hydraulic power divided by the shaft power. So you can see this. The pump input power or the pump shaft power is hydraulic power by pump efficiency. And what is the power drawn? Electric power drawn by the motor itself is the pump shaft power divided by the efficiency of the motor. So these are the simple equations that we'll be using. Now, as we said, when the pump is inefficient, when we determine, okay, we do measurements and we determine that the pump is inefficient, it is not the problem with the pump alone. The pump may be all right, but how well it is matched to the system, that is important. So what is a system? So system is basically, for example, here you see a tank with water. Then we are pumping this water by the pump going to the overhead tank. So let's say we've got 15 meters height. The overhead tank height is 15 meters from the pump. So what it means is, in this case, if the pump is going to pump at 10 meter cube per hour, it has to raise to a height of 15 meters. Overhead tank is 15 meter height. If the pump is going to pump at the rate of 50 meter cube per hour, again it has to lift the height of this 15 meters. So this is a 15 meter, what we call it as static head. Vertical height from the pump discharge to the delivery of the tank. And if you're going to pump at 100 meter cube per hour, again it has to go to a height of 15 meters. So irrespective of the flow rate, the static head is going to remain constant. It doesn't change with the rate of flow. There is another type of head which you will encounter. Say we have a river is flowing, and we are taking the water by using a pump, and the pump is horizontally pumping it to a reservoir, a tank in the center of the city. Now here in this case, you will find that it is a horizontal transfer of the liquid. There is no vertical displacement. There is no vertical lift. In this case, the static head or the vertical height to be lifted is almost zero. Whatever the pressure gauge is going to show here is basically the resistance offered by the pipeline. So there is a pipe, and what is the resistance across this pipeline? It is given by the Darcy's friction factor, which is 4FL V squared by 2CD. That means the friction in the pipe is proportional to the square of the velocity squared. So in this case, the diameter is constant, so that means it is also proportional to the area squares. So whatever the flow rate or the friction factor, friction that is going to occur in the pipelines, that is proportional to the square of the area. Or area is constant, sorry, this is area is constant, so we make it as square of the flow. So HF is proportional to the square of the flow. So here it means that if you're going to put 10 meter cubed of flow into the pipeline, it is going to have this much of friction. If you're going to have 50 meter cubed of flow into the same pipeline, this is going to be the friction head. If you're going to put 100 meter cube, this will be the friction head. So the pressure gauge actually shows the system resistance, the resistance offered to the flow by the pipeline. And this is parabolic, obviously, because it is proportional to the square of the flow. So it takes a parabolic form. This is a pure friction head. That means a system without any static or vertical lift. So only horizontal transfer of liquid through the pipeline. But normally in a typical industrial situation, you will find that there is a little bit of static head as well as friction head. So a cooling tower system, for example, as we have seen, the cooling tower will be like this. Then you will have a pump. So the water comes to the pump, and pump is pumping to the various processes here. And then the return water is coming back to the top of the cooling tower. This is a case where there is some kind of a static head, which is the vertical lift in the cooling tower. Then the friction will drop across these pipelines, these heat exchangers. All this constitute the frictional component of the pressure drop. Okay, so this is a case with some static head and some frictional head. So in this case, the static head is very high, frictional head is very less. So there could be other cases where most of the cases it will be like this, a little bit of static head and a large amount of frictional head. This is a typical industrial situation you will come across. Now, whatever we have seen so far is in relation to the system. This is called the system curve. The system curve has nothing to do with the pump. It is a curve which shows how your system will behave if you put in different quantity of liquids. So we have seen what the system curve is. Now going to the manufacturer. The manufacturer sells a pump. The pump has got a curve which is called the pump characteristic curve. This is a pump curve. Pump curve is like this. As we have seen initially, the less the head, the more the flow. So as we keep on offering more resistance, head increases and flow decreases. Now the operating point is where your pump curve meets the system curve. That is this point. So this is our system curve, and this is going to be our operating point. So this is operating point. We may have several pumps in the market which will pass through this point. So the operating pump which will satisfy a requirement is the one which will pass through this point. There could be another pump which again can pass through this point, perhaps like this. So which of these two pumps should we select? Then we try to find out what is the efficiency of this red pump at this point. What is the efficiency of the blue pump at this point? Whichever is maximum, we choose that pump. So at the operating point, the pump should be operating at the best efficiency. So this is called the best efficiency point. So at the point where the system curve meets the pump curve, and the pump has the best efficiency at that point. So there are several pump sizes available. Normally manufacturer, for a typical casing, he will put several impellers. Like here you have an 8-inch impeller, 7 point, the same casing, different size of impellers are provided to make it big or small. So these are all, as you can see, they're all parallel to each other. In this case, the pump characteristic curves. And these are the ISO efficiency curves. So which tell you whether your requirement can be met by a very efficient pump from this family of pump curves. This is one family of pump curves. For one particular casing, different impeller. If you're not happy with that, then you can go in for another set of family of pump curves where possibly you could get a better efficiency. Now let us look at this example. So we have a pump to be chosen. How to select a pump? We normally asked all the users how much is the requirement for water in different. Let's take an example of a centralized cooling water system. The cooling tower water is going to different parts of the plant. Section A, section B, section C, like that. We ask each section how much water do you need. So each one calculates how much the water requirement. So section A calculates maybe 20 meter cube, but they're not going to say we want 20 meter cube. They would like to keep some margin. So they say 30. Section B, the requirement is 40, but then they say 45 or 50 meter cube per hour. So like this, every department keeps adding the factor of safety or the margins, and then finally the project engineer who is going to select the pump, he looks at the design data and maybe 300 meter cube is the actual requirement. But he is also not confident, so he adds his own margin of safety, say 400 meter cube, goes to the dealer. Dealer doesn't have that 400 meter cube per hour pump. He's got a 500 meter cube, big pump he's got. And he's offering to give it at the same price as that of a smaller pump. So 500 meter cube per hour pump is purchased, and the purchase man is also very happy, looking at the future requirements. He feels that it can serve the future requirements. The bigger pump always is better, and for a cheaper price he is getting. So we bought a big pump. The big pump has been installed and it is going to deliver 500 meter cube. It delivers 500 meter cube per hour as you start the pump. Efficiency, we have ensured that it is maximum. So it's about 82% here. Now, as you start operating the pump, you find that the requirement is only 300. The pump is now delivering 500. The requirement is only 300. So how to make this 500 meter cube per hour pump operate at 300? Which means we have to throttle the pump. So the simplest thing is to close the valve a little bit. So when you close the valve, so what happens here? So you're going to take it like this. Increase the head. Closing the valve means increasing the head. So now we are closing the valve. And we have increased the head from 50 to 70. Pump is facing a higher head. And as per the characteristic curve, the pump delivers a lower flow rate. So whatever desired flow rate that we want, 300 meter cube, we've got it. What happens to the power? We have come from this point to this point. So at this point, the power drawn was, let us say, 55 kilowatt. Okay. Now we have throttled the pump. The efficiency has come down from 82 to 77. What will be the power here? As we measure the power, we find it is only 45 kilowatt. So what has happened? By throttling, we have reduced the power consumption. So can we take it as an energy conservation measure? Have we saved energy by throttling? How did we get the lower power here? After throttling, it should have increased the power. After reduction in efficiency, it should have increased the power. But then here we are getting a reduced power. This happens because the flow rate has reduced. So as you have seen the first pump curve, as you increase the flow rate, the power also increases and vice versa. So now it is not against the same flow rate we are comparing. Earlier it was 500 meter cube, 55 kilowatt. Now it is 300 meter cube and it is 45 kilowatt. So it doesn't mean that we have saved energy. Now, what are the options? Suppose if you had gone in for a smaller pump, say 300 meter cube per hour pump we have selected, then the pump curve would have been this blue curve. Exactly cutting the system curve at this point, delivering 300 meter cube per hour. So if this was the case, then here it would have been 55, this would have been 45, and this would have been maybe 30 kilowatts. So we should have been drawing only 30 kilowatts, ideally, if we had properly selected the pump, rightly chosen the pump. Now, how to get this blue curve? We got a big pump. This is a common in many other industries. We find that the pump sizing is oversized pumps, and ultimately resulting in this kind of a situation. So many of the plants prefer to run it with a throttle condition. So in any case, it does not affect the process. The requirement is met, everything is going smooth and fine, so not much of concern is there. So this requirement of some change in the pump or some change in the operating characteristics will be known only when you do a measurement. So now 300 meter cube, and the options are going for a smaller pump, you get 30 kilowatts. Otherwise, it would have been 45 kilowatts with throttle, 45 kilowatts. So this can also be, instead of a smaller pump, of course, you bought a new pump, big pump, you can't change for a smaller pump. So you trim the impeller or take out the impeller and keep it in the store, buy a new smaller impeller and put it inside the casing. It will be this blue curve. The other option is sometimes you want 300, sometimes you want 400, sometimes you want 200. So these kind of fluctuations or variations are there in the process. Then what are the options? Then the best thing is, since there is a varying requirement, as the name suggests, the ideal option will be to go in for a variable frequency drive. So which will have many speeds. The pump will operate at different speeds, and for each speed, the pump characteristic curves will be like this. So this is at full speed, reduced speed, further reduced speed, and another reduction in speed. As you see, when you reduce the speed, it's almost like operating a small pump. So we get the blue pump also by reducing the speed of the pump. Right. So now let's look at another classic example. So we have a requirement. The requirement here is 68 meter cube per hour, and the head is 47 meters. We have 5 choices: A, B, C, D, and E. Which of these pumps should we choose? If we choose A, then at this point, the head is here. At this point, you get the required flow rate, 68 meters. But the system head is only 47 meters. So for 47 meters is the system head, and your requirement is 68 meter cube, which means you have to throttle this pump, keep on throttling, increase the head. So it reaches 76 meters, then you get 68 meter cube per hour. Efficiency is going to be 50%. Okay. Now, if you choose B, C, D, all the same thing will going to happen. You're going to throttle. But if you choose the pump E, so the pump E, when you operate, it will deliver 68 meter cube per hour at 47 meter head. So the pump E, if you use, you don't need to throttle. You get the desired requirements without throttling the pump. What is the impact between A and E? How much will be the difference in power consumption? If you choose A, it will be 31 kilowatt. If you choose E, it will be 16 kilowatt, almost 50% save. So right selection of the pump is the key to energy savings. So if you look at this calculations, how did we get this 31 and 16 kilowatt? And the equations which we have already seen, the flow into total head, into the density, in the gravitational constant by 1000. So get hydraulic power is 8.7 kilowatt. Divided by the shaft, the efficiency of the pump, you get shaft power, which is 14.5 kilowatt. Divided by the motor efficiency, you get the motor drawn for 16.1 kilowatt. Similarly here, everything is the same except for the head. Head here is 76. In the earlier case, the head was 47. So this change has led to an increase by almost 50%. So now you're drawing, the pump is drawing 31 kilowatt. Everything else remains the same. Now what is the impact? So if you see, the life of the pump is about 20 years. Now what will be the impact of this oversized pump? The difference in power consumption is 14.9 kilowatt, and if you're operating for 1 year, this is the amount of additional energy that you're going to lose. In terms of money, it is about 10 lakhs per annum. 10 lakhs per annum, and then you calculate for 20 years how much money you're going to lose. So that's about 200 lakhs, which is about 2 crores. In a 20-year lifespan of the pump, what you'll be losing is 2 crores. So in this example, the extra cost of electricity is more than the cost of purchasing a new pump. Maybe every day you can purchase a new pump. So that's what it means. So a small, little bit of oversizing can lead to huge losses. But this goes hidden. We don't know whether it is happening or not unless we measure the efficiencies. We find out what is the power consumption, what is the hydraulic power. All this calculation needs to be done. Then you arrive at the actual power required for a pump. So as we have seen, a bigger pump, if you want to make it smaller and reduce the power consumption, one is you can trim the impeller. Trimming the impeller means reducing the diameter of the impeller. In a typical pump, the flow is proportional to the diameter. The head is proportional to the square of the diameters. And the power is proportional to the cube of the diameters. So when you reduce the impeller by 25%, impeller size from 8 inches to 6 inches, the power consumption reduces by almost 50%, more than 50%. So a huge potential for saving is there when you identify a bigger pump and you want to change the impeller. When the impeller change should be adopted is when you know for sure that there is always a fixed volume or fixed rate of flow of water, but reduced rate of flow of water is required, and that is not going to vary with time. Then you go in for an impeller change. The other option will be to go in for a speed change. If you want a varying requirement, as we already discussed, this is 1480 RPM, 1350 RPM, and 1184 RPM. So the pump behaves like a smaller pump at reduced speeds. So depending on the requirement, you can change the speed and make it suitable for the needs, required needs. What is the impact of a VFD? So in many of these applications regarding the pump, we will find that the VFD is a very useful gadget with which we can control the pump speed and optimize a lot of energy. Here is a case with throttling. So the first initially it is operating at this point, maybe 1,400 gallons per minute. This is a full speed it is operating at this flow. This is the power, 16.7 kilowatt. Efficiency of the pump is 87. Then we throttle. We want only 1,000 gallons per minute. So we throttle it. We throttle. we get 13.4 kilowatt. Efficiency slightly drops. We want now 700 gallons per minute. So at 700, we further throttle. Power consumption is 11.6 kilowatt. Efficiency is dramatically down, 70%. So imagine we are putting a VFD for this pump. We want the same variations to be met by a variable frequency drive. So which means initially the pump is operating at full speed. So at full speed, there is no change. So same 16.7 kilowatt. And when you're going to 1000 gallons per minute, we reduce the speed to such an extent that we get 1000 flow rate. And at this point, you see the power is only 6.4 kilowatt. When you reduce it to 700, somewhere here, okay, so the power keeps further coming down to 2.3 kilowatt. So 2.3 kilowatt at 700 RPM. You look at the efficiency, still remains at 86%. No change in the efficiency. Whereas for the same 700 here, when you throttle, the power is 11.6. So 11.6 versus 2.6 here, 2.3. So you can see the difference which VFD is able to accomplish. Efficiency also here it is 70%, here it is 86%. So with the VFD, the advantage is that the efficiency more or less remains the same. It doesn't affect the efficiency. At the same time, why there is a huge dramatic drop in power consumption is basically because of your okay. So we've already seen that your power is proportional to Q of the speed. So if you reduce the speed by 20%, the power will come down by 50%. So this is the affinity law. The flow is proportional to the speed, head is proportional to the square of the speed, and power is proportional to the cube of the speed. Okay. And impeller diameter, not very popular these days because VFD itself has become so cheap. Earlier days, before the advent of the VFDs, most of the companies were looking at the option of the impeller diameter change, but now it has been taken over by VFD, which they feel is much safer and also economical. And with an impeller diameter change, as you reduce the diameter, the pump behaves like a smaller pump, just like the speed change. Right, now let's look at some case studies. So the other things are some of the issues which we've already discussed, and I think significant about it. It's the operation of the pump. Now let us come to energy efficiency part. Now this is a case study one, flow optimization, the condenser cooling water circuit. Now here are these pumps. It's a 8.5 megawatt biomass based power plant. So you have a turbine, condenser. Turbine is discharging the steam in the condenser. On the other side, we have the cooling water circuit. The cooling water is pumped to the condenser, goes to the cooling tower. Cold water again comes back to the pump, sent to the condenser. Now, this is the system. And the pump, 90 kilowatt pump, and it's got 1470 RPM. These are the characteristics, nameplate rating of the pump. Now, the company had a VFD for these pumps. So we are operating two pumps now. The original RPM is 1470. Now we are operating at 1400 RPM. At 1400 RPM, the pump is drawing 70 kilowatt. The important thing is when you're operating these two pumps with the VFD, both these pumps should operate at the same speed. If one is operating at a higher speed and the other one is operating at a lower speed, then this pump will not be able to pump water into the header because your head is proportional to the square of the speed. So when you reduce the speed, the head also comes down. So in order to effectively utilize the VFD in parallel pump operation, it will be ideal to have a common VFD for both the pumps. In case it is not possible, you have a separate VFD, but then ensure that both the VFDs are operating at the same hertz or the same speed. So they synchronize with each other and pump adequate quantity of water. Now it is at 1400 RPM, drawing 70 kilowatts. And the temperature, inlet temperature of the condenser is 28 degrees centigrade. Outlet 36.7. Well, power plant, these cooling towers, most of the power plants have a range of even 10 degrees. So this cooling tower was designed for a range of 10 degrees. So here it is, okay, 28 is going, 36 is coming. Still there is a possibility of increasing the range. Now the delta T is 8.7 degrees. Now what we're going to do is we're going to reduce this RPM further. So in the second case, we reduce the RPM to get a delta T of 10 degrees. So we make the necessary reduction in RPM. We find that we have got this 27.9, 37 points, so 10 degree delta T we have achieved. Corresponding to the RPM is 1300. So 1300 RPM and the power here is only 55 kilowatt. So by reducing 100 RPM for these pumps and increasing the range of the cooling tower, we are able to save this much of power. So the annual savings by operating at this point is 2,40,000 kilowatt hours, and monetary savings is about 20 lakhs. So at the same time, we have to ensure that the vacuum in the condenser is not disturbed. There's one important parameter which has to be simultaneously monitored. So as you reduce the flow rate, there is a possibility that sometimes the vacuum, so you keep on reducing. At one point, you find the condenser vacuum going up, getting more pressurized, so you stop at that point. And that is the point what is given by this 1300 RPM. Okay, this is one. And similar case here. So you may have a refrigeration plant, 337 TR. From the refrigeration plant, the refrigerant is coming out, going in the condenser. The refrigeration condenses. What happens to the cooling water? So the cooling water comes here in this direction, it goes and then into the cooling tower. 315 meter cube per hour is the flow rate. So 25 degrees and 27.7. So this is outlet actually. So the difference again, same, the range of the cooling tower is only 2.7 degrees, which means that the flow rate is very high. So the delta T is only 2.7 across the condenser, high, indicating high flow rates. So in this case, it is designed for a range of 5 degrees. That means this delta T across the condenser is also the delta T across the cooling tower, which is the range of the cooling tower. Now we have this VFD for this pump. So we operate this pump at different speeds, 1485, 315 meter cube per hour it is operating. This is the hot water temperature, cold water temperature. Okay, so this is one is 25 and 27.7. Okay, and the power drawn for this speed is 29 kilowatt. As we reduce the speed, so keep on reducing the speed till again you optimize on the power consumption for the compressor. Discharge pressure of the compressor is to be monitored here. Keep on reducing the speed, flow rate keeps on coming down. So this is the power consumption at the most optimum speed of the condenser water pump. Earlier at full speed it is drawing 29 kilowatt. Now it is drawing only 11 kilowatt. So this is again, when we are studying pump, many times cooling water pumps, it has to be studied in conjunction with the process as well as the cooling tower performance. This is another interesting case, how measurement can help in identifying some of the losses. This is a power plant, a gas turbine power plant, 32.5 megawatt combined cycle power plant. So the steam side of the power plant, we have the steam turbine dumping the steam in the condenser. We are circulating the water, and the condensed steam or the condensate is coming to the hot well. From the hot well, you have condensate extraction pumps which are pumping the water to the deaerator. So there are obviously two pumps, CEP1 and CEP2, condensate extraction pumps. And here, to a surprise, we found that both the pumps were operating. Normally, one pump is operating, one pump is a standby. In this case, both the pumps are operating. So we had an ultrasonic flow meter. So we measured here at this point. As you measure, we find that this is 40 meter cube per hour. At this point, if you measure, it is 43 meter cube per hour. So, but when you put the measurement here, this shows only 40 meter cube per hour. 40 here, 43 here, you should have got 83, but you're getting only 40. Then you go for tracing. What has happened? Where is this excess flow going? And there's a maze of pipelines. In this figure, it is very obvious. There is a recirculation valve here, back to the hot well. So this recirculation valve is normally closed, but it was passing, and part of the flow was going through the recirculation valve back to the hot well. It was creating numerous problems, and the company actually started in terms of thinking of replacing this pump, thinking that the pump is worn out. Manufacturer also suggests that you should replace the pump. The purchase order is going to be placed. Then we find this is the issue. Then this recirculation valve was rectified. So one pump was switched off. It's a very simple case. Sometimes measurements can help also in identifying some stray cases where energy losses take place due to some malfunctioning of some of the gadgets. So in this case, one CEP, each CEP was drawing about 26 kilowatt and one CEP was switched off. And this is another simple case. So this is a water treatment system in a chemical plant. You have a bore well. So the company was operating a bore well. The bore well was pumping the water to the tank, a raw water tank, which was above the fire pump house. And this, from the raw water tank, the water was taken by a pump and it was first aerated. Spray nozzles here, aeration was done. When we asked the plant people, what is the purpose of aeration? Why this process is there? Then, of course, the water treatment person also not very clear. So we had a discussion and we later on found out that earlier, the water for this was taken from a river. So there was a river nearby. The water was taken from the river to this water treatment plant. And that river water had plenty of iron content in it. So in order to remove the iron, this aeration was done. But today you find there is no trace of any red colored particles anywhere in this area. Red colored particles indication that iron content is there. It's very clean water, clean. Why do you want to pass through these nozzles? So the first question, why analysis? Why is this required at all? When you have changed the source of the water from river to bore well, so that means this aeration process itself is not required. Now this water is again pumped to a pressure sand filter. The pressure sand filter filters all the suspended particles, then it goes into a filter water tank. And from the filter water tank, it is taken for treatment further for DM water. So where DM water is made, so we have two sources of supply: filter water and DM water. And as we measure the suspended solids, total suspended solids here is well below the limit. So this pressure sand filter was also not required. Now, many cases where we find that, something which has started maybe several years back, continuing to be operated without, of course, the functional requirement or the functional need. So by doing this reassessment of the system and re-engineering the system, these two pumps were totally avoided. So very simple case. You don't need to do any major changes except for minimum piping. And this is a case of open circuit pump where in a rolling mill, a steel rolling mill, we have cooling water which is directly in contact with the output material. So initially the ingots are punched, there's a calibrator, there's a piercing press, elongator. So it goes through several processes and it needs to be cooled. The bearings, the rollers, all this needs to be cooled, which means the water is in direct contact with all these materials. So the direct contact water has got a lot of iron particles. So it comes here into the scale pit. From here you pump the water using two pumps, 45 kilowatt. It goes into a settling tank where the oil that is coming along with the water, oil particles in terms of lubrication, the rollers, all this comes along with the water. So oil floats, skimmed and taken off. The remaining water goes to the hot well. From hot well, there are two pumps which pump to the cold well through spray nozzles, spray ponds, you can say. So the spray ponds, evaporative cooling takes place, the water gets cooled, and this is again pumped back to the process. This is the process. Now, if you see the actual process, what comes out of the furnace, the billets or the ingot, it's the time between one to another is about 7 minutes. So the water supply is continuously on. Requirement is only for maybe a few seconds in each of these processes. So the water supply is continuously on for 9 minutes, which means on the average, the temperature that comes here is about less than 30 degrees. So 30-degree water comes, the hot water sump, again you're trying to cool spray pond, maybe it comes to 28. So it makes no sense because all these processes are at around 1500 degrees centigrade, whether it is 30 or 35 immaterial. So what we decided was to make a change to this system. So here, as you can see, the hot water was coming at 30 degrees in the process, cold water going at 28. So after modification, what is the modification we did? So we provided a bypass here to the thermostatic control. So the water will come here. When it is greater than 34, it will go to the hot well. When it is less than 34, it will bypass in the cold well and directly it will get pumped into the process. So it keeps on circulating, water becomes 34, it goes to the hot well. So otherwise it will short circuit and go into the cold well directly. So this 2 into 55 kilowatt pumps, we don't need to operate continuously. So that itself is quite a huge savings the plant could get. And finally, the last case study here we have is for the hydraulic power packs. So many of the engineering industries, they use this hydraulic power packs. So this is a hydraulic power pack here, what you see. And so here, as you can see, this is a cold extrusion process. The cold extrusion process so this is a cold extrusion process which requires hydraulics. The hydraulic motor is continuously in operation. Okay, and the requirement is not continuous. So material moves, there is a elongation that is taking place, and there is an idle time. So if you see, the hydraulic motor requirement is only for 30% of the time. Remaining 70% of the time, it is idling. So there is a bypass to the hydraulic control, bypass back to the tank. So in that process, significant, it is a 75 kilowatt motor. It is consuming about almost 42 kilowatts during the idle operation. This requires some careful planning. So we need to do a cycle times analysis, list down the various processes where hydraulics are required, how many seconds or minutes this pressing or elongation will be required, and what are the idle times, and how we can use perhaps a VFD. In this case, a VFD was used. So when there is no need, no action is taking place, reduce the speed, avoid completely the bypass circulation of the oil back to the tank. So in this case, as you can see, there is before VFD, this used to be the case. So initial start. So when the requirement is there, the power goes to this point, and this is the idle operation. During the idle, in the idle situation, there is a bypass which is happening back to the tank, and and then there is a peak required. During elongation, there is a peak that happens, and again it falls down. So there's a cycle. After providing the VFD, this peak, the initial peak was there anyway for the various operations, pushing and pointing. Then, when there is no need, we have reduced the speed of the hydraulic motor. So you can see the power has drastically declined here in this idle period compared to this. So you can see this. Then, of course, you have the peak when VFD, using a pressure controller, you can actually do this. When the valve opens, the pressure drops, and immediately the VFD picks up the speed to provide the necessary pressure for the hydraulic circuit. So these are all some of the examples just to tell you about the various opportunities in the pumping system. Of course, in every industry is unique. You find that plenty of cases exist where you can save energy in the pumping system. And replacement of pump is something which we should keep it for the end. Before even replacing the pump, with the existing pump and the system, how do we optimize the system side? Then come to the pump. So can we retrofit a VFD or regulate the operation of the pumps? So in this process, I think majority of the scope lies in this process. So we don't need to bother about replacing the pump itself. Motor, less said the better, as we've already discussed. We don't have to even about the motor at all. So the pump system, start with the system, come to the pump. Between this, you will find there is at least about 30 to 35% saving potential in all these pumping systems. Okay, with this, I'll end my session, and thank you very much for listening. If you have any questions, we can take this.
Sir, this is Varun. There are few questions posted in the Q&A, this one. So
Yeah.
I'll pose the question one by one to you, sir.
Yeah.
The first question is, what is the maximum design efficiency of centrifugal pumps, and how much maximum you have observed in practical?
Yeah, it depends on the size of the pump. The bigger the pump, the more the efficiency. We have seen pumps having efficiencies as high as 82%. So 82% efficiency pumps are there, but the normal range of pumps maybe somewhere between 11 kilowatt and 37 kilowatt. The efficiencies are around 70%. The bigger pumps in the oil industry, you have huge pumps for water injection and all that. It even goes up to 85%.
Thank you, sir. The second question is it preferable to install VFD for a system with high static head and less friction net? And in case of high static head, I think parallel pumping will be preferable instead of VFD. That is his question.
Yeah. See, high static head. What are we talking about? You have a underground sump, like in your domestic households. We have a sump at the bottom. We have an overhead tank. The pump pumps the water from the sump to the overhead tank. The case of static head. But this is not the only case. What about the boiler? The boiler always requires a constant pressure. Suppose you are operating the boiler at say 9 kg per centimeter squared. The pressure required is constant. When you, for example, provide a VFD for the boiler feed water pump, what will happen? Say you are using a 10 tons per hour boiler. You are operating at 9 kg per centimeter squared pressure. Now the steam requirement has come down. It is going to be 7 kgs per centimeter squared. So normally you are using a recirculation valve. Now if you provide a VFD for the boiler feed pump, so as we have seen, the flow is proportional to the speed. You reduce the speed by 30%, flow comes down by 30%, it reaches 7 tons per hour, which is a requirement. From 10 tons per hour, you come down to 7 tons per hour. But what about the pressure? The boiler is already operating at 10 kg per centimeter squared. You reduce the speed of the pump. So the head of the pump also will come down. Now the boiler head has come down to maybe as low as say 6 kg per centimeter squared, whereas the boiler drum pressure is 7 kg per centimeter squared. So it will not be able to pump the water into the boiler, which means wherever there is a high static head, you have to apply VFD with caution. In a case like domestic, where you want to just fill the tank, it doesn't matter. You don't need a VFD. You just need to have a level controller, if at all. So when it reaches at a particular level, you switch off the motor. That should be the option. But high static applications, the VFD may not give you the full benefits. As we have seen, the power is proportional. The Q is the speed. It doesn't apply to high static head applications. Boiler feed pump, you can have VFD. It is there in many applications. But if you want to keep the pressure constant, you have to do it in a combination of VFD plus the control valve. Both should operate and ensure that the pressure is kept constant. At the same time, the flow is reduced. So in such cases also, you may not get the full benefit of VFD. Power is not proportional to Q over the speed because there is also a throttling involved partially. So in these cases, some kind of caution has to be taken. Yeah, next question, Varun.
Does pump impeller material have impact on efficiency, like SS, bronze, etc.?
No, the material, whether the bronze impeller or a stainless steel or cast iron impeller, it all depends on the liquid that the pump is going to handle. So nobody chooses a material of the pump for the sake of efficiency, and it does not have a big impact on the efficiency. It's basically the profile of the impeller which determines the efficiency. And we also heard in many cases, the coating for the pump. What if we coat the impeller? So there are epoxy coatings which are being done to the pump impellers. But one thing which we keep repeatedly saying is that if you are going to put some money for energy efficiency, if you're going to make some changes, you should ensure that the savings are measurable. Before and after, you should be sure that you have saved energy. Only in such cases, we would advise you to put money into your energy efficiency activities. When you're not sure, somebody says, I'll quote the pump, I'll give you this pump. Well, it may be, for the life of the pump, it may be good, but efficiency doesn't change at all. I mean, we have seen many cases where there's no great change in efficiency by coating of the pump. So material does not have any big impact on the efficiency.
The next question. What is the IS or IEC energy efficiency class for energy efficient pumps?
What is the
IEC energy efficiency class for energy efficient water pumps? Is there any IEC efficiency class for water pumps? He's asking.
No, I don't think IEC doesn't apply to the pumps. maybe the IEC class is applicable for motors, but for pumps, we have never come across such a universal standard for efficiency. Each manufacturer declares its own efficiencies. So there is nothing like a class of pumps with a particular efficiency.
Or IS. He is asking whether it is IES or IS.
No, IS not necessarily for efficiency, but pumps have IS classification. But unlike the B has got star rated appliances for star ratings for different appliances like transformers, motors, and all that. But for pumps, I don't think you have such a standard classification on the basis of efficiency alone. So my knowledge is not there.
Okay.
Yeah.
The next question is, does the VFD adjust itself as per throttling?
Does the VFD adjust itself as per throttling? Huh?
Yes. Maybe he is meaning that auto control.
Yeah. See, what are the important aspects? This again we are seeing in the industry many times that people have put up a VFD. How to control the VFD? When to change the RPM? How to change the RPM? This is an issue. So in many cases, it is open loop. They have put a VFD and okay, they are operating at 50 hertz, thinking that VFD by itself will save energy. It doesn't. If you put a VFD and operate at full speed, it will consume more energy because VFD itself has got a loss of about 5%. So it consumes more energy if you operate at 50 hertz. Then we have seen, okay, some pumps. So we have set it at 45 hertz. We have put a VFD, we are operating at 45 hertz. What is the basis? Nobody knows. Say for a simple cooling water system, what should be the basis of control? So we have put a VFD for the pump. The pump speed has to be regulated. What should be the methodology? So in this case, cooling tower, what is important? What controls the flow? What is the purpose of cooling tower? It takes away some heat from the process and throws it out into the atmosphere. The heat taken away is a function of your mass flow rate of water and the delta T, that is the range of the cooling tower. Now, mass flow rate, if you want to decrease, if you can decrease, then you can save power on the pump. So when the heat flow, when the heat to be transferred is the same, if you decrease the mass flow rate, the range will increase. Suppose the operating range is 2 degrees in a cooling tower, it does not mean the cooling tower has got a problem. It means there is not sufficient heat load in the process, more flow is going into the process, so the temperature rise is only 2 degrees. So the heat dissipated to the cooling tower is a function of the heat load in the process. So now what we can do is we can have a differential temperature controller. You measure the cold water temperature, you measure the hot water temperature, you set a control parameter. Delta T should always be 5 degrees. This delta T always 5 degrees logic, you give a feedback to the VFD. So VFD senses the delta T is more, going more than 5 degrees, it increases the speed of the pump. The delta T is going to be less than 5 degrees, decreases the speed of the pump. So these are the controls that needs to be worked out depending on the application. What needs to be controlled and what will tell the pump at what speed I should operate. Yeah.
So the next question is, which method can be best suited in the flow controlling of parallel heat exchangers whose operation is based on batch production?
So I understand that there are 2 heat exchangers.
Yes, sir. Yeah.
Yeah. So the 2, can you repeat the question?
Which method can be best suited in flow controlling of parallel heat exchangers? He has not mentioned the number of heat exchangers, it is parallel heat exchangers whose operation is batch process.
Okay, so let us look at, we have about, let's say, 4 compressors, water cooled compressors, and only 2 are in operation. But the water continues to keep going through the intercoolers, aftercoolers of the standby equipment also. The same thing happens in the chillers or DG sets where you have 3 or 4 equipments, only 2 are in operation, 2 are not in operation, but in those standby equipment also the water is circulating. So this idle circulation, how to stop? That means there has to be a solenoid valve. When the equipment starts, the solenoid valve opens, the water is sent to the equipment. So otherwise the solenoid valve will shut and prevent the water from flowing. This again, how will you control the pump? So if you are cutting off the supply to two of the equipments in operation, you cut off the two equipment supply, the water flow in the other two equipments is going to increase. So which means you have to have a pressure controller. So you have a pressure controller, you close the valve for two equipment, the other two equipment pressure increases. That you give as a feedback to the VFD of the pumps. So it will help to regulate the speed of the pump and save energy. Okay, next.
Sir, what next question is, what are different type of sensors available to feedback the pump operation with VFD in a auto loop?
Yeah, that's why you have a pressure controller, temperature controller. You can even have a flow controller. So it all depends on what is your requirement, what is your process, what needs to be controlled. Sensors are available for anything. The only thing is you need to identify what needs to be controlled and what is the range that you want. So accordingly, you can give a feedback to the VFD.
Sir, next question is it possible to use VFD for thermic oil circulation with uniform supply?
See, thermic fluid, we have explored this option in many of the cases, especially many of the textile mills which use thermic fluid. They'll have about 30 kilowatt or 55 kilowatt pump. And so let's say there are 3 or 4 equipment to which the thermic fluid is supplied. Say 4 dryers are there. So out of 4 dryers, sometimes if all the 4 are operating, then at that time there is no need for a VFD. Suppose if 2 dryers are off, only 2 dryers are on, then you need circulation only for the 2 dryers. So can we reduce the speed? Can we cut out the supply to the idle dryers and reduce the speed of the VFD? It's possible. So you can reduce the speed of the VFD, but only thing you have to check whether, because at reduced speed, the flow of the thermic fluid reduces into the heating coil of the thermic fluid heater. So accordingly, you have to have fine controls which will control the temperatures. Because earlier, some mass flow was flowing through your thermic fluid heater. Now, reduced flow rate is going to flow. But if the firing rate is going to be the same, then the temperatures will shoot up. So with that precaution, you can approach. That is one. The second thing is where VFD can be applied for a thermic fluid pump is, suppose you have a shift operation. Night shift you are not going to operate. Only 2 shifts you are going to operate. 10 o'clock, all machines are shut. You cannot shut down the thermic fluid pump because the thermic fluid has got this property that you cannot immediately bring it to a stop at high temperature. The oil quality will deteriorate. So what is suggested by the manufacturer is that it should be kept continuously in circulation till it reaches, say, 30 degrees. Which means no equipment, the entire factory is closed, but thermic fluid pump is in operation, continuously circulating the oil. Here the requirement is that the oil should be kept in motion. It has to keep moving, it should not be stagnant. So it need not move at a rapid rate, full speed, but the pump is not required. So during this period, we can put a VFD and reduce the speed of the pump so that just about little bit of movement is provided, which will not affect the quality of the oil. So these are the potentials for thermic fluid VFD applications.
Okay, sir. So next question is, when we can consider using multi-stage centrifugal pump?
Multi-stage pumps are required where the pressure requirements are very high, like your boiler. So boiler pressure requirements, set even 10.5 kg per centimeter square boiler. The 10.5 is a big pressure. for a centrifugal pump. So a single impeller cannot achieve that. So we have a series of, it's almost like putting continuously booster pumps. Output of one pump going to the input of the other pump, like that. You have series of pumps, say 8 or 9 pumps in series. The same thing is accommodated in a multi-stage pump. Multiple impellers. Output of one impeller goes as input to the other impeller. So continuously there's a pressure building takes place. So the output you get about 10.5 kgs pressure, which is required for the boiler. So boiler is one application. Then you have the high pressure pumps, which are used for cleaning the meshes in the paper machine, or you have hydraulic systems which can work for elongation of tubes in a rolling mill. So those are all very high pressure pumps. They work even up to 40 bar, 50 bar, like that. In such cases, multi-stage pumps are required.
So the next question is, normally what is the life of the pump? How to decide on the replacement?
Life of the pump depends on you. You decide when I should change the pump. Either the pump dies by itself, which normally doesn't happen unless you have a very corrosive or erosive liquid. The impeller getting damaged is remote. The next thing is where the pump can go wrong is when there is a cavitation. So especially if the pump is handling high temperature liquid, it can be subject to cavitation. So cavitation is like putting some gravel or stones inside the pump and operating. If you get that kind of noise, it means the pump is cavitating. You'll find this often happening in pumps handling hot water. So under such circumstances, pumps by themselves get damaged. Otherwise, to replace a pump is in our hands. When to replace a pump? Suppose the pump is 10 years old. Should I replace or not? What are the options? How do you determine? See, one simplest thing is, can we measure the efficiency? If we can measure the efficiency of the pump, nothing like it. What is the existing efficiency of the pump? Then you go to the market. You find out from various manufacturers. For the same head and flow, what are the various options available? Efficiency available. So if there are better pump, because maybe 10 years or 20 years down the line, several changes have taken place in the manufacturing of the pump itself, leading to better efficiencies. And if perchance the same pump, same ratings, has got a better efficiency, the modern technologies, then of course that's an option. But again, the most important thing is merely changing the pump does not guarantee you efficiency. You have to look at the best efficiency point. Is the pump operating at its best efficiency point? That is the purpose of efficiency determination of the pump. It is not necessarily with respect to changing the pump. Pump has been designed, it is operating. Is it operating at the best efficiency or not? So if the pump is not operating at the best efficiency and then you decide to change the existing pump by a new pump with the same flow rate and head, the new pump also will give the same efficiency, the old efficiencies, whatever you're getting with the old pump. Because it's not a problem with the pump. It is a problem of matching the pump with the system. So selection of the pump, as we discussed, that's why we spend a lot of time on the selection. The importance of selection can never be underscored. So first is the matching of the pump, then you look at the higher efficiencies, whatever is possible in the market. Okay, next.
I think we can end the question and answer session. That's all, sir. You've answered most of the question and answer session.
Okay, any other questions, you can always mail us and we'll be glad to answer you.
Yeah. So thank you for your wonderful session.
Yeah, thank you very much to everybody.
I'm sure participants would have found this interesting and really worthwhile. So I request the participants to keep seeing our website for the updates on the various webinar schedule. And I also request the participant to share this information with others so that they'll also be richly benefited. So, sir, DG sir, Mr. Santosh, DG sir wants to address. Hello.
सर अभी पता करता हूँ.
हाँ.
सर डीजी सर मीटिंग में गए हुए हैं, ठीक है आप
Okay.
Thank you, Dr. Nagesh Kumar.
Thank you very much.
You gone beyond the mandate and valiantly tried to answer all the questions. And you can any further you want to say any further information before concluding?
No, only thing, if there is any other question which has been left unanswered, probably they can mail it to us so that we can address them separately through the mails.
Fine, sir. That we'll be able to do it, sir.
Yeah.
Thank you. Thank you all the participants.
Thank you. Thank you all.
Thank you very much.
So thank you, sir.
Thank you very much. Yeah.